The next type of random variable is continuous random variable. It is a measurement instead of counting the success. Suppose we are making a pen and the length of the pen has to be kept as 10 centimeters. But all the parameters over the machine, the skill of the operator, uh, material, everything has been very controlled. But in all the controlled conditions, we cannot always expect 10 centimeters. It can be 10.1, it can be 9.99, it can be 10.2, it can be 10.01. So this occurrence, which has no reason for deviation, is called randomness, as we have already explained in the previous lectures too. Now, the matter is that this occurrence we are basically recording. And when we are recording, it is called as continuous random variable. And the probability of occurrence, depending upon the minimum size possible of the pen to the largest size possible of the pen, will be called the domain or the sample space of the continuous random variable. If we are throwing a ball, it can be minus infinity to infinity. But when we are manufacturing a pen, it can be from 0 to, suppose, the maximum length of the material supplied. So that will be considered as domain or the sample space of the random variable. Over that domain, there are no fixed point of occurrences. That is why it is called continuous probability distribution. So in this case, we are not able to have bars on the probability distribution. We will have area covered by a particular curve that we will see in the theoretical explanation of continuous probability density function. Look here, please. Now see, this is the distribution x over x-axis and the probability as a function of x over the y-axis. That can be any kind of function. There is no fixed rule for any distribution. Distribution can be like this. Distribution can be like this. Distribution can be skewed on one side. So there are different shapes of distributions are possible. Maybe like this. So many shapes are possible, but this is a continuous range. What we see here, the possibilities are from 0 to infinity. But in general, when we consider a continuous probability density function, we consider a distribution having the possibility of occurrence from minus infinity to infinity. Midpoint anything, the mean value for the x, and this y-axis is nothing but the relative frequency, which is called as probability. Now see here, in this case, because we are not able to find out the probabilities based on the summation of the function, we have no option left other than integrating over the range. So if you have to find out the probability for x, whatever it can be between a to b, suppose length of the pen, if I say that what is the probability that it will be between 9 centimeter to 11 centimeter, but we were expecting it to be 10 centimeter as a mean value. So what is the probability? We have to integrate the function, that is nothing but the curve over here. This curve is basically dependent upon a function. So that function may be called as continuous probability density function. Now this function can only be considered as probability density function when it satisfies this basic condition. In case of discrete probability distribution, we had the summation from x0 to infinity, but in this case we have minus infinity to infinity. Integration has to come as 1. This 1 is nothing but the, just change the color and see what is 1. 1 is let's take blue. 1 is nothing but the area under the curve over the range from minus infinity to infinity, or in some cases it may be 0, some cases it can be minus infinity. So this 1 is nothing but the area for the total sample space of the random variable x. If you have to find out a probability for between two points, you can integrate the function over the range. If you have to find out the cumulative probability here, then cumulative probability is nothing but the probability of x a. Suppose, but here there is no need for equal to sign, because it is very difficult to distinguish the difference between 10.0 and 10.0001. So no difference is possible. That is why the less than and equal to is having the same meaning as less than, and the similar case for the greater than. So this probability is nothing but the integration from minus infinity to a fx dx. See next, this is an example. We will solve it and we will understand how to use the continuous probability density function. Come on the workspace. See this example here. What is the problem? Problem is the total number of hours measured in units of 100 hours that a family runs a vacuum cleaner over a period of 1 year is continuous random variable x. So this is in measurement of x is nothing but 1 by hundreds of unit. And this is 100 hours. So unit, which is, if there are 100, x is 1 unit, that is equal to 100 hours usage. Now see here, this is a function having probabilities x 0 to 1, then 2 minus x for 1 to 2, and then 0. Suppose I want to draw this probability density function. This is x 0 and 0, 1, and then 2. So from 0 to 1 there is a function x. So this will be a straight line. A straight line y equal to x. This is fx. And from this point, when it is 1, you are reaching the point 1. For 2 minus x. So for the equation 2 minus x, definitely we are nothing but this particular point. So this is 2 minus 1 is 1, and 2 minus 2 is 0. So you are getting as 1 here, and then you are getting 2 here. So what is the area under the curve? When you see the area under the curve, how much area under the curve? Curve is nothing but a triangular shape. So area under the curve is half into base is 2, height is 1, that comes about 1, which is nothing but the integration minus infinity to infinity fx dx. But we have calculated using the area of the triangle method. See here. Now, if we use the conventional method as we learned here, find the probability over a period of 1 year a family runs their vacuum cleaner less than 120 hours. So for A part, see A part, they want to know the probability when x is less than 120 by 100, because it was x is the 100th part of the hour. So this will be probability of getting x less than 1.2. So what is this? Minus infinity to x fx dx. That will be equal to minus infinity to 0 fx dx plus 0 to 1 fx dx plus 1 to 1.2 fx dx. That gives, this is nothing but 0 as over here, 0 to 1. So 0 to 1 the function is x. So we will have integration 0 to 1 x fx x dx plus 1 to 1.2. This is 2 minus x dx. That will give you the probability as x square by 2 0 to 1 plus 2x minus x square by 2 0 to 1, sorry 1 to 1.2. So this is 1 by 2 plus this is 2 multiplied by 0.2, this minus 1 is this, then minus bracket 1.2 square divided by 2 minus 1 square divided by 2. So that is 1 by 2 plus 0.4 minus 1.44 minus 1, so 0.44 divided by 2, that will be 0.5 plus 0.4, 0.9 minus 0.22. So that will be the probability for this function, comes as 0.8 and 7 minus 2 is 5.58. Now if we want to see this over the curve, then 1.2 will be somewhere here. So definitely it is going to cover the region which is this one. So this area under the curve is nothing but representing this probability. Now see the second part, what they want is, what is the probability that family runs their vacuum cleaner between 550 to 100 hours. Now see here, change the color, part B, see here, probability that x is between 0.50 to 1.0. That will be probability 0.5 to 1.0 fx dx. Now we have to see which function from the main equation has to be followed. So 0.5 to 1 will lie in the first part of the equation. So it is nothing but only x over here. So 0.5 to 1.0 x dx. That is x square by 2, 0.5 to 1.0, that will be 1 by 2 minus 0.25 by 2, 0.75 by 2, that is nothing but 0.375. Obviously, this is, if we see over the curve, this area is nothing but 0.5 will be somewhere here, 0.5 to 1, so that is the area over here. So this particular area under the curve is what we are looking for in the second part of the problem. Now, this is how we see uh, the procedure for calculating the probabilities for continuous random variable. See another example. I will solve in short over here. An important factor in solid missile fuel is the particle size distribution. Significant problem occurs if the particle sizes are too large. From production data in the past, it has been determined that particle size in micrometer distribution is characterized by fx for x more than 1. So it will be some distribution after 1, there will be some distribution. So this may be some equation for 3x to the power. Verify that this is a valid density function. For the first part of the problem, this equation minus infinity to infinity fx dx equal to 1 must be satisfied. Let's see here. Minus infinity to infinity 3 fx dx will be equal to minus infinity to 1 fx dx plus 1 to infinity fx dx. See here, it will give us a value. This term will be 0 as per equation, second part of the equation. The first term, second term remains 1 to infinity 3x to the power minus 4 dx. That will be equal to 3x to the power minus 4 plus 1 upon minus 4 plus 1. That for from 1 to infinity. So this will be minus 1 upon x to the power 3. 1 to infinity. That comes as one upon infinity minus minus plus 1 upon 1 cube. So this term will be 0 and that comes about to be 1.0. Hence we can say that fx is a valid probability density function. Now, in case this is a valid probability density function, we have to find out in the second part cumulative density function. For cumulative density function, this is nothing but fx is an integration minus infinity to x fx dx. which I will consider minus infinity to 1 plus 1 to x fx dx. This term is nothing but equal to 0, but this term is 3x to the power minus 4 dx. So it will be nothing but 1 upon x cube minus 1 upon x cube 1 to x. So it will be 1 minus 1 upon x cube. Your fx is cumulative density function is 1 minus 1 upon x cube. Third, what is the probability that random particle from exceeds 4 microns? There are three possible ways. The third part, probability that x exceeds 3 microns. There are three possible ways. One is 1 minus probability of getting x less than 3, which is nothing but equal to fx equal to 3. Or we can integrate from 3 to infinity fx dx. So if we follow this procedure, this will be equal to 1 minus 1 upon x cube for, and there x is 3, so it will be 3 cube. So that will come as 1 upon 27. Probability that x will exceed 3 microns. This is an answer of the third part. This was all about handling continuous probability density. I think these two explanations, one about uh, discrete probability distribution and another about continuous probability distribution, will help you to understand the concept of relationship between random variable and its probability of occurrence. Either it is simple through probability density function or through cumulative density function. In continuous, we can only calculate the area under the curve using the integration method. But in discrete random variable, for the case of discrete random variable, we can sum up the height of the bars, which represent the probability of occurrence of the respective value of the random variable. That is all. Now we will discuss joint probability distribution function when there are more than one random variable in a process. Thank you. Good luck.